Okay, so this is the moment where I still have to check if the connection is stable because this is OBS connecting to YouTube and there are lots of shenanigans. I think we're good though. Yeah, I can see myself.
Okay.
Great, we're in. Muting myself there, hitting play though, and let's refresh that one more time because then I can see what people might be talking about. Great. Hi everyone, welcome to another live stream on behalf of Probable. If you could let me know where you're calling in from, that is always grand and fun. This week, we are going to talk about this different project. Long story short, I've noticed some things on LinkedIn, and I also saw this GitHub repo of this new project called Model2Vec. It deserves to be said that I'm still kind of an NLP nerd. So I've done a lot of NLP in the last couple of years, and this project does something very cool in NLP that I think could also be somewhat relevant for what Scikit-learn is doing. Because the main theme of this project is we're going to see how lightweight we can make transformer models for embedding purposes. In my case, I'm mostly interested in classification. But you can also imagine people are interested in these embeddings for like more of the retrieval kinds of tasks, like vector databases and that sort of a thing. But primarily what I'll be doing is I'll be basically just having a look at what we can do with classification here. But before going into, like, I ran some benchmarks that we're going to talk about that I think paint a pretty good picture of how this works. But before going in there, I figured it would also be good to just discuss the theory a little bit, because we have to understand how these transformers work internally a little bit before we can fully appreciate the trick that the authors of this Model2Vec library have done. One small thing I do want to mention before diving in, like this has been getting a fair bit of attention. Like, it's only got almost 300 stars, so it's not GitHub stars is not always the right measure, but sentence transformers, like the big embedding library, that has been adding support for this work. So like the idea is definitely sound, and also let's just discuss kind of what they're doing here. Make this full screen. That way I have kind of a nice, pretty canvas, and let's turn this into a markdown cell. It's just kind of, okay, I have to type something in there. Okay, space, there we go. And then this gives me a nice white canvas to draw on. But yeah, do still tell me where you're from. That's always good to know. People from Sweden. Cool. Oh, okay, a bunch of new places. Oh, and by the way, I see that Tom Aarse is in here. He's the maintainer of sentence transformers. Do all say hi to Tom. He's doing good work maintaining that thing, because that thing is big. But okay, like very sort of super quick introduction. Why do transformers matter? Imagine, if you will, that I have a time series task. So I've got X over here, right? And I'm gonna be interested in predicting some sort of Y parameter over time. Then you can imagine that this is maybe a noisy data set. So I'm just gonna draw out some dots here, let's say. And let's say that you're interested in making like some sort of a prediction. Well, then to maybe add some more context, depending on the task that you're doing, maybe one thing you can do is you can apply kind of some sort of smoothing, where the idea is you're going to do some, let's say, I guess we can call it a kernel, but there's basically this Gaussian thing that moves along this axis over here. And let's say you want to make a prediction for this point over here. You're just going to take some sort of a weighted average of all the points according to this kernel that moves over. So you can say, oh, at this point, stuff that's very close gets a high weight, and stuff that's far away gets like a lower weight. And, you know, we can kind of come up with different ways of doing this. You can come up with a thinner one, you can come up with a thicker one, but you can imagine, at least, by doing this averaging trick, you do get kind of a smooth curve in this time series. But another way of phrasing everything that I've just said is, if I want to have like good context over here, like if I want to make a prediction, if I want to like have a good way of figuring out like, hey, what's a good prediction here? You could maybe say, well, let's turn it into an attention problem. Let's say that I am over here somewhere. What data points matter most to me? And can I come up with a nice way to sort of weigh those things such that I can say something intelligent about where I am? And you could look at that as saying, oh, that's just calculating a weighted average, and that's fine. But I would like to maybe rephrase that and saying, well, it's kind of an attention mechanism. from this point, you're basically saying which points do I give more or less attention to. That's a way to sort of rethink what is happening here. And the keyword of attention here is going to matter because we're going to talk about because this is like fairly standard stuff you can do in time series land. It's not super duper complex, but you can wonder, hey, this whole attention mechanism thing, can I do something like that in NLP as well? But then I'm dealing with tokens as opposed to time series. But the idea of attention is still the same. You're just trying to figure out some sort of interesting way to add context. So let's say I've got some sort of a sentence then instead. So I'm no longer dealing with a time series. I'm definitely doing sentence stuff. So I could do something like, oh, I don't know. I pet my cat. I don't know, some sort of sentence. Then let's then pretend that I've got token 1, token 2, token 3, and token 4, let's say. Well, if I'm going to add context here, I can come up with a better. Let's go for a better example, actually. So let's so same idea. I'd have a better example. So I have money on the bank. This is the classic example, and I've got bank of the river. This is a better example, actually. Yeah. So the reason why this is a better example is you'll notice that both of these two sentences have the word bank in it. And that's great, but they have totally different meanings. Like, I could argue, like, if this is token ID 15 in my dictionary of tokens, right? I guess you could associate the same token to both, but in order to associate some sort of a meaning, I need something extra. I need something more. And yes, this Tom is right. I'm also Dutch. Definitely feel free to associate my examples with where I'm from. Dutch people, famously, we battle rivers all the time, so the bank of a river is a relevant term. Having said that, though, how do I, like, suppose I've also got an embedding for this. Like, I've got embedding 15 for token 15, let's say, and I've got some sort of a lookup table that says, okay, token goes in, vector comes out. What's the vector here? Well, what I could do, just kind of on a high over level thing, I could maybe say, well, if I want to get more context onto this embedding over here, and if I want to get something such that these two embeddings that I get out over here, that's kind of different, then what I need is an attention mechanism. What I'm going to do, again, is I'm going to look at other tokens in the sentence to see if I can add some context. And we're not going to be able to come up with some sort of a Gaussian curve to define what would make a good attention mechanism. The whole idea behind time series is, well, stuff that's close, that's usually maybe relevant, because stuff that's further away is further into history, so that's less relevant. But in the case of sentences, well, we kind of need a mechanism to figure out the amount of attention that we should give. And that's what these transformer architectures in the end do. The whole point with the transformer architecture is that there's basically a neural network of sorts that's just going to be able to say, okay, for this embedding over here, or for this token over here, this token has an embedding. Okay, is this embedding going to be relevant? Well, maybe not so much. Is this one going to be relevant? Well, maybe not so much. Oh, but this money one, yeah, let's, we have a neural network in between over there, and I'm doing this kind of in a hand-wavy way, but we basically have some sort of a mechanism, and that's what a transformer model does, to sort of do intelligent reweighing of vectors by sort of taking clever means, I guess you could say, from different tokens in the sentence. That's one of the, I would argue, bigger mechanisms inside of transformers that kind of allows it to do the context thing. And you can hopefully also imagine if we have some sort of a system that can figure out, oh, hey, these tokens are less relevant, this embedding from that token that is relevant, that is going to give us more intelligent embeddings as well, because that will allow money on the bank to be different than bank of the river. Even though the banks in both cases have the same token, you can definitely argue that we are able to sort of have our attention be different because different embeddings appear in the sentence, and there's mechanisms to deal with that. Okay, so super big picture idea here, and I wish I could have the time to go more in depth, but I don't. But this is kind of what transformers do. They have this attention mechanism, and that allows you to do clever reweighing of all of these vectors. So, bon, we understand that. That's kind of cool. The downside of doing stuff like this is that you do need a pretty big architecture. And in the end, what you are going to do is you are going to sort of have some sort of a mechanism that compares this embedding with all of these. And you're basically doing all of these comparisons of all these embeddings. And that results in some pretty big matrices that got to multiply. So you could wonder, well, can we maybe do something clever instead? Like, can we make this more lightweight? Because we like the fact that there's this attention mechanism. We like the fact that we can do all these clever things. But for a lot of use cases, you sometimes need a GPU in order for this to be pragmatic. So can we do something clever is kind of the question. So we're going to move towards Model2Vec there. And again, like I do apologize a little bit because I need to be a bit hand wavy in the interest of time. But if there are like questions, feel free to ask. But I'm now going to try to translate this towards the observation from the Model2Vec framework. So you can imagine this is a transformer model, right? So transformer model, TFM. And it kind of starts by these tokens that go in. So we've got tokens on this side. Inside, there's lots of attention stuff happening, right? And then we kind of get these tokens that come out. And let's call this, we will call this embeddings, but let's add the word context here as well. So these are kind of like contextualized. These are embeddings after they've been treated with a bit of attention, etc. And maybe, you know, when I say tokens go in, of course, I kind of mean the embeddings of tokens. There's an embedding step that happens before that. But you can also imagine afterwards, there's like another transformer layer, maybe, depending on the model that you have. You might have more of these transformer layers stacked on top of each other. All that stuff is well and good. But you can at least see, like, okay, embedding, like, we start with tokens, and in the end, we still have embeddings that can kind of come out, and they will have been treated by all this attention stuff that's been happening in the middle here. But the observation from the Model2Vec team is still, hey, hang on, we still have a token kind of going in on this end, and we still have a embedding going in on this end. And we have a tokenizer, so we've got these tokens, so that also means that we've got some sort of a vocabulary, if that makes sense. Like, deserves some extra attention, actually. So if I have, so the way that tokenizers work in transformers, by the way, suppose I have the word geography. I should have maybe started out with that. So you've got the word geography and you've got the word geology. Let's take those two words. You can imagine that, yeah, these are two different tokens, but the word geo is in both of them. You can also kind of imagine that geo has a lot of meaning. So with the tokenizer for these BERT models, what they actually typically do is they kind of have like a compression trick internally, such that you don't actually have tokens, you've got subtokens instead. So maybe instead of representing geography, you can have geo, gra, and phi. I can imagine this is like a sort of a vowel that happens a lot. Geo, law, G, let's say. And maybe also have got like, I don't know, geography. And again, you've got like geo, you again have gra. Sorry, I meant to say geology. Geographics, I don't know. But hopefully you get the point. Like, if we do this compression step beforehand and we figure out all these subtokens, that's going to be useful because we don't have to remember every single word out there. We can just make do with subwords. But still, we have a vocabulary, we have these subwords, they go in here, they get turned into some sort of embeddings, we have the attention mechanism, and per token, we still have something that goes out over here. Sometimes these transformer architectures, they also have like some sort of a pooling mechanism, such that you can have like a sentence embedding that's contextualized. All that stuff is totally cool. But the main observation here, at least, is, you know what we can still do? We can still like look at the vocabulary, just put like, and kind of like just put one token in here. Just put one token from the vocabulary in here. And kind of just see what comes out. And, oh, hang on, there's still a mapping from like token to embedding that kind of goes out. Maybe what we can just do is we can just loop over the entire vocabulary and just use this transformer in the middle there to give us a better embedding in a way, but one that has lots of attention mechanisms attached, I guess, and like it has seen different kinds of data, and the way we get to that vector embedding is a different training procedure by all standards. But maybe those contextualized embeddings carry some extra value that's a bit more than what the standard embedding techniques would offer. That's kind of the direction or the vibe I got, at least, when I was exploring the paper in the library. I thought I saw, like, I don't know if I saw a paper actually, but like the documentation page is pretty elaborate on this. And so this is an interesting question. You can kind of wonder, well, does this work? And we're going to discuss a few benchmarks that I did to sort of confirm that. But I do also want to mention like some extra stuff that you could do here. So one thing that you could do on the embeddings that come out over here, like let's say that the embedding here is of size 1024. One thing you can just go ahead and do is you can just do some PCA. Besides having the benefit of like normalizing your data, because the PCA also does some central, like it centralizes some things. But one thing you can also then do is say like, okay, let's just have size 300. Let's go for like smaller embeddings. That way we can keep it lightweight on disk. You know, fair. But what you can also do is you can kind of do a reweighing trick. What you might be able to do is you might be able to say, well, some of these subtokens, they just matter kind of more than other subtokens. If you have a subtoken that's going to be used everywhere, then it might be a bit more of a stop word. And this is a phenomenon that's described as Zipf's law. And I kind of want to just grab the Wikipedia page of that, because it's a pretty interesting phenomenon in linguistics. Zipf's law. There we go. And this is just kind of a like empirical thing that people have found out about. So when you can I get it for linguistics? Yeah, okay, there's a formal definition, there's some empirical testing. Maybe I should add the word linguistics. There we go. Yeah, so like the main observation, I guess, formally, if you sort all the words, like this is the most frequent word, this is the second most frequent word, and this is etc. I guess this is a nice chart. So if you just look at the most frequent words in English, the, of, and, like those are the most frequent words. Then you'll notice that it's almost exponential in the sense that the most frequent words just get used so much more often than the non-frequent words. And maybe knowing that up front can also help us say, well, these vectors are more important than other vectors. We can add a weighing factor that reflects that. And that's sort of the Zipf's law trick that's been mentioned in the repository as well. So if you go to the, again, if you sort of go to also their like pretty picture that's here on the site, you've got your input tokens, you do the transformer thing, and then for those input tokens, you've got basically an embedding. Then you apply PCA and some zip scaling, and then you've basically got like just an embedding model that's super duper lightweight. That's kind of the thinking here. So yes, you still use a transformer architecture, but it's really only used once to generate these embeddings that you then store on disk, and those are super quick and fast to retrieve. That's kind of the thinking. One extra detail is if you scroll down, I think you can also see a chart at some point where, or was it on a blog post? I forget. Let's go to the website. No, where is it? I saw a chart. Hang on, I want to find it now. Is it on the blog? I remember seeing a chart. Yeah, that's the one. So what they claim, and it reflects my findings. My numbers were super different, but this chart really does match my vibe. What they found is that if you do this trick where we just store everything on disk as embeddings and sort of check the performance, they have some sort of accuracy for classification tasks plotted here. The higher this axis is, the more accurate it is. And basically on this axis, they say the number of samples per second that we can just dump through. So on both cases, higher means better. So we find that over here, we've got the most accurate model. This is the second most accurate model, but they can't handle many samples a second. And they don't use a GPU. They do everything on a CPU over here. And these two would be very popular sentence transformer models. That's so all mini LM L6 V2, that's I think the default. And this is becoming like a very popular, I don't think it's a default, but it's becoming a popular one, this BGE base ENV15. These two models give you the best accuracy in this benchmark, but you'll notice that they are just dead slow, basically. What they then do is they compare that to byte pair embeddings and glove embeddings. So these are, you could argue, old school word embeddings, basically. And you can see that, yeah, there's a drop in accuracy for both of them, even though they are a fair bit quicker. But you can also see that their model, it is able to handle basically the most samples per second. But they do tend to be just slightly better performing than the normal text embedding model. So there's something about the transformer model, then doing PCA and then applying Zipf's law, apparently, that makes these at least somewhat competitive to the more performant models, mainly because they're just like orders of magnitude faster. That's kind of the observation here. And for some use cases, that might actually be fine. And I will, in particular, make a point for Scikit-learn. So Scikit-learn pipelines are typically revolved around these, yeah, I think that, but yeah, tabular is like the main thing that they're used for. That's like the main original use case. You can also use them for other stuff, but tabular, I think, is like the main thing. And it could be the case that you've got some tabular data, but as part of that tabular data, I don't know, maybe there's like a sentence of text in there or something. But it's not really an NLP use case because, yeah, there's some text in it, but the text is but like one column of the entire thing we're trying to go for. And then maybe this could be an alternative to just using count vectors. That's kind of the thinking here. Like it's because it's so super duper lightweight. If you wanted to introduce a transformer architecture just to do one column in the big table, like that might not be worth the effort. But if you look at the speed over here, this might. Like that's the observation, at least on my end, that makes it interesting. And the fact that we are performing a fair bit better than the sort of old school word embedding models, that's also a plus. Because it also means I don't have to use the super old libraries as well. So that's also a thing I like. So I'm just going to check if there's questions and I'll answer them. But hopefully this has been like an okay introduction into theory. Like this is why I was initially interested in testing out this Model2Vec stuff. Partially because I'm from the background of NLP that really likes to keep things lightweight. If I can not need a GPU, I'm a happy person. But I also want to really point out that from the Scikit-learn perspective, there's a lot of stuff that I really don't mind here either. These are like features I tend to like to see. So there's one person that's asking like, hey, why are they doing UMAP instead of PCA? I cannot speak on their behalf because I wasn't part of this effort, but I can imagine why PCA would be a good candidate. For one, PCA keeps the linearity intact, and that's like the UMAP totally breaks that apart. So PCA is basically just a matrix that you're multiplying to some sort of embedding, and yeah, you can take the inverse, and that's all well and good. When you're doing UMAP, that's a non-linear mapping, basically. And kind of as a side effect of the non-linear mapping, UMAP tends to be great when you're interested in clustering, but we are not necessarily interested in clustering here. We're just interested in not losing a lot of information while still having smaller embeddings. But the clustering thing is maybe not necessarily what we're interested in. Another thing you can imagine with UMAP, the global information is lost. I did a live stream on UMAP a while ago. Feel free to watch that if you haven't, if you're interested in going deeper. But you can kind of imagine if something works super well in the big embedding space with logistic regression. If you then apply PCA, odds are that the logistic regression will still work because the logistic regression is just a linear model. The plane just has to move a bit, and you're kind of good. But in the case of UMAP, it might not be even certain if logistic regression will work in the first place. Again, because it's gonna really try to keep clusters together, but the distance between clusters has no meaning. That's the big difference. And in the case of PCA, we're not going to be as good as clustering, but the distance between blobs of data will have appeared in the global structure as well as in the local one. That's kind of the main difference, I would say. Check the live stream I did on that topic if you're interested in going deeper. There's like visualizations I spun up to sort of demonstrate that point a bit. But yeah, okay, let's talk about this little benchmark I did. So it's one thing that I read something and I like what I read, but then it's always good to just kick the tires a bit and see if you can reproduce some of the results. And that's what I've attempted to do here. So I have the Model2Vec library loaded up over here. Let's zoom in a smidge. So what you can do is you can basically say, what I'm doing here is I need some sort of name that's easy to read. And this is the name as far as sentence transformers is concerned. So I can give that's the model name that I'll also be using. This goes into the sentence transformers. It can do the sentence transformer thing, but this Model2Vec library has a distill function that will allow you to basically just grab any transformer model. It's going to then loop over the vocabulary of the transformer model, fetch the embedding for each token, so to say, and then it's going to apply the zipflaw trick, as well as going to apply PCA. And then you can basically save that as a pre-trained vector embedding model on disk. And you'll notice that what I'm doing over here is I am not just doing this once, I'm doing this a bunch of times. I'm gonna be interested in seeing like, hey, if I have very few, if I really do a lot of PCA, like turn it to like 16 vectors, lose a lot of information, or if I keep it somewhat big, what's the difference? And I also want to measure the effect of that Zipf's law trick. If we do this, if we do the reweighing based on Zipf's law, can we, do we get like better classification results? I was kind of curious about that. So I do this a whole bunch, loop over both of these two models, loop over all these different settings, and that's going to lead me to store a whole bunch of stuff on disk. So I've got the Model2Vec, name of the embedding model, 16 dimensions, don't use Zipf's law. Model2Vec, base model, 32 dimensions, yes, use Zipf's law. So every single one of these folders represents a pre-trained model, so to say. So it's like the pre-work that I did for this task. Tom is saying interesting things. Oh, first, Elias is saying, could this be a suitable replacement for fast text? I think so, if only because fast text is now archived, unfortunately. One thing I do want to say about fast text in particular, I still think you can get like very good pre-trained models for non-English. Like there's, I think they had like 170 languages supported, if I recall correctly. So you can definitely still use it, but it's archived. I don't expect there to be a lot of support for that English, just because there's more training data and budget available to research it. So I'm going to say yes, it can replace fast text, with the caveat that you want to check the language. That's something I cannot guarantee. Tom, okay, so this is funny. Tom Arce is saying, I'm pretty interested to see whether Model2Vec scales well with really long texts. We're going to get to that. Because that's also something I've noticed, and it's also I had a quick chat with the maintainers of the project, and this is a theme that we're going to get to in a bit. But yeah, the length of the text, as we'll see in the benchmark in a bit, definitely has an influence. And I've got some theories on that. But let's just talk through the benchmark first. So I have all these folders. I've got all these model paths, so that's all good. Then what I'm going to do is I'm going to open up a data set for a project that I've got. This is a data set called new dataset sentence.jsonl. And let me explain that data set first. This is totally a hobby project that I'm about to present, by the way. Archive front page. So on GitHub, I have this basically this news app that I made for myself. It's a GitHub Actions job, and every day it scrapes archive, the big paper repository, and it tries to find papers that I might be interested in. The way it works is I have a classifier that just looks at every single sentence, and it tries to predict whether or not there's a sentence that suggests that a new dataset appears in a paper. In my experience, if people took genuine effort to create a new dataset for a new task, something interesting is usually happening, and usually I'm interested in reading that article. So to train this system in particular, I need a dataset that just has these annotations, like, hey, here's a sentence. Does that sentence suggest that the article might be containing a new dataset? Yes, no. That's what this dataset is about. So this is a dataset for this task for my personal project. And let's just have a quick look at some of the examples. New data JSON. I think it's at the bottom over here. So new dataset sentences. There we go. Yeah, so there's a sentence here. Our code and dataset is available here. Okay, there's a category new dataset 1. So that's one. Yeah, and here it says we train our model on the new synthetic image dataset that we release. I don't want synthetic datasets. I'm only interested in like the like actual human-made data sets in this one, so that is a false label. And there's a bunch of these examples. I think I've got like a few thousand of them. Yeah, like 2,200 or so. Yeah, so a sentence like these findings may assist researchers, regulators, and automated vehicle developers attempting to evaluate safety driving automations. Okay, great. That sentence is not about a new data set, but this is something homemade. Like I annotate this data set myself. That this is a data set that I maintain for my own purposes. So that is what this data set is about. It is basically every line here is a sentence, and it's just a yes or no label. Is this about a new data set? That's the task. So, what I'm doing then is I'm using the sentence transformers implementation here. I'm saying, hey, let's load up a static embedding. And then the static, or actually I'm not using that. I'm using static model directly. But basically I'm loading up those, I'm able to load up a model path like I have over here. And that is able to give me like X that goes into whatever machine learning model. So here comes yet another for loop. Given that I have a representation for my data, what I can do is I can calculate the cross-validation score because I can follow that up with a machine learning model. And I'm going to be comparing logistic regression with a histogram gradient boosted classifier. That's what I'm doing over here. That gives me lots of these scores. And after that, I'm gonna I have a look at one of these rows. I can see like, okay, this was the base model. I've got the number of dimensions. I've got yes, no. So I've got my own little data frame library that can deal with generators called lazy lines. I'm basically doing polar stuff here. But in the end, I'm able to make this chart. And I have different data sets that have similar charts. So we're just going to have a look at this. But what you can see over here is the blue line is one embedding model. So I've got the blue line over there, and I've got an orange line over there. That's the other embedding model. So these are just the two embedding models from sentence transformers that I distilled the information from. Then I've got, is it dashed or not? And if it is dashed, then it is using the zip-slaw trick. If it is not dashed, then it isn't using the zip-slaw trick. And then besides that, I've also got the number of dimensions on the x-axis over here. So this is how much PCA do I apply? Do I allow for a lot of dimensions, or do I really just care about like a few? Now, in this particular case, it to me feels like zip-slaw is not really doing much, although it does depend a bit on the model that you pick. At least on the logistic regression side, it feels like zip-slaw might just be making things worse, which I didn't really expect. Another thing that I also find just slightly humorous and interesting is that in tabular data land, usually using a boosted histogram model is seen as a better practice than using a logistic regression. But in NLP tasks, if you just have an encoder and you follow that up with any model, I have found a bunch of times that logistic regression is actually state of the art. Like it's hard to beat. And that's kind of what I'm seeing over here as well. It just kind of feels like the linear model on this task is just doing a fair bit better than the boosted histogram, which is very unintuitive if you're a Kagler. You would not expect that. But in this embedding NLP stuff, it actually does seem to be the case. It also seems to be the case that it just kind of converges a bit quicker over here, but all right, like no matter what, like I do get some results that are pretty good still. Like I get to like close to 90% accurate, which is nice. Like that means if I were to put this in production for my app, it's going to be able to say like this sentence, does it say data set? Yes, no. Like, okay, you can kind of build a small little app around that. You get into the ballpark of useful there. So that's good. But you gotta wonder, how much better or worse is this compared to one, just using a bag of words model, something that just says, well, this token doesn't appear yes, no, and then build a model on that. And two, I want to compare this to just using sentence transformers directly, because we're still distilling from sentence transformers. I would like to know that number as well. But okay, let's say with logistic regression, getting like between 88 and 89% accurate, that's something we can get with this model on this task. What happens if I scroll down? So I need to be a bit mindful here, but here I am just using sentence transformers old school, so nothing really weird or scary. But I'm just going to say, hey, here's the the full BGE model, the full base model. And these models are actually also kind of in that ballpark, a little bit below maybe, but it's definitely same ballpark. It's like 88%-ish, which is kind of what I see over here as well, both on linear regression and on the ensemble model. And if I were to just do, and honestly, if I were to just do count vectorizer, which the count vectorizer gives us sparse data that comes out, so I cannot give that to the gradient boosted model because that model needs dense data going in, so I'm only able to compare that with logistic regression. But there, I also seem to be getting like 88% or so. So, okay. Although I still think it's pretty interesting that the ensemble model performs worse than the logistic regression one, it might also just be safe to say that this is just an easy task. So seeing a difference in the model performance here, maybe we shouldn't sort of double down on that. Maybe I should go for a slightly harder task. Because also, if you think about how many ways are there in a sentence to mention that the paper you're going to read contains a new data set, there's only so many ways to do that. So maybe this is just kind of an easy task, if you think about it. Like, does the word data set appear in a sentence? If so, it's probably about a new data set, right? So like, okay. This is an interesting benchmark. I was particularly interested in seeing the Zipf's law doing worse here, but all right, maybe this benchmark doesn't tell me everything, right? That's also kind of a good feeling to have here. So then I went ahead with a different data set. This is the insults data set. This data set comes from my previous employer. Like if you go on their GitHub repos, they have a couple, like I used to work for a company that makes this tool called Spacey. And there's a couple of these like demo data sets that you can play with. And one of these data sets, Enos, there's also a video of her that's like 7 years old now. But it's basically this data set of Reddit comments. And we're trying to figure out if the Reddit comment is an insult or not. Like that's the task that this data set is all about. And I did a typo there. So, but just to give like a example of a text, I am reminding the crowd over here, this is Reddit data. So I'm, yeah, so this is about parenting and someone being somewhat rude. But then the question is, when is rude being an insult? Like that's kind of the whole idea behind this data set. And you can also imagine like this is kind of a harder task. Like there's nuance plays a role a bit more here. One thing I am also curious about is just from collections import counter, because that is also something that I didn't check beforehand, but maybe I should have. It's just a class imbalance. Right, so there's one thing to also remember, this data set, I think the other one as well, it has a fair amount of class imbalance as well. Like in the end, thankfully, most of the examples in this data set are not actual insults, but they might contain bad words. Like that can still be the case. If you say a sentence like, oh, he acted like a prick, that's something different than saying, oh, you are a prick. Like those are two different statements. So, you know, at least from a distance, I can argue this just kind of feels like a harder data set. So what's the result going to be? Is it different? And let me just grab the results are just in some ways very different, but in a lot of ways it's also not that different. So one thing that is the same in both of these two situations is that Zipf's law does not do a good thing for logistic regression here, and I seem to see the same pattern over here. That's kind of good to know. One thing to remember is that the previous data set had about 2,000 examples in it. This one only has 500. So yeah, that might explain some of the jittery stuff that I see around over here. Like it does feel like maybe before doing this benchmark, before calling this benchmark proper, maybe we should collect more data first. That said, one thing that I do see is that in this particular case, the ensemble model actually does a little bit better, especially when we allow for higher dimensions. And that's interesting because that suggests to me that in the embedded space, there might be like these two clusters that are far away from each other, but they do require a different splitting plane in order to split. And you can kind of imagine this is kind of like the XOR problem that logistic regression tends to be pretty bad at. So if I have like just a very simple example, if I've got green dots over here and if I got red dots over here, then logistic regression is going to have a field day. Just, put a splitting line between, you're good. But if you have a situation where in two-dimensional, you've got some data over here that's green, some data over there that's green, and you've got some data over here that's red, and some data over here that's red, then you're in a kind of world of trouble, because there's no single line that you can draw here that would perfectly split up the data. And this is a hunch, but like I can imagine it in embedded space. You might be dealing with multiple clusters if you're thinking about this insult task. If you're like, I can see Tom being interested in this maybe more than the average person because he's also knee deep in NLP. But hopefully you can also kind of imagine, sometimes in embedded spaces, it's not just one cluster that you're interested in detecting. Maybe there's multiple of them, and especially if there's like nuance, there might be more than one way to say something, and that might also mean that multiple pockets have to sort of be detected in that space. And that is something that a ensemble system is better at than a logistic regression. So I thought that was just kind of an interesting observation that might kind of explain what we're seeing here. Again, I kind of came to the conclusion of, all right, this is kind of interesting. But again, this is not necessarily a full benchmark. One thing I did do at the end over here, so we, like the highest performing models of around 80% or so. And we do get slightly higher if we just go with the base models, and we get slightly lower if we go for the count vectorizer model. So one thing that I do think is interesting about this particular example is that this is just so in line with, I think the website should be, no, not the website. We want the blog. Yeah, so this blog post, like if I look at this chart over here, then I would say like, yeah, what I'm seeing in, even though this data set is too small to call it proper benchmark, some of the stuff that I'm seeing here when I compare it to like the actual transformer models, this one in particular is doing, that's actually kind of interesting too, right? So you can see that the ensemble model, it also performs like, I would argue, significantly better on than the logistic regression model. If we don't do the Model2Vec thing, if we just go to sentence transformers, then we also see that the ensemble model just works way better. So that is actually like super interesting. And if I look at the count vectorizer in this particular case, that also performs worse than what I'm seeing over here. So again, I kept this in because I did feel like the interesting thing about this data set is that it does totally fit with this picture. And although it's like a small-ish data set, I do like it if I see reported numbers appear in a paper or blog post that I seem to be able to reproduce the feeling of locally. That does give me the idea that, okay, they're kind of reproducing something over here, right? So, okay, so far so good. The final benchmark that I figured I might do, and this is like the hard part here, is like, what is a good benchmark? Like, what text data do you get? And I figured I might start with something that I would use personally myself, but then I also started thinking, like, that sentence detection thing that I made, that is a short data set. Like, I'm just doing sentences, so it's like a short text. And yeah, I have lots of examples, but that's not the same as having like a paragraph of text. Like, that's kind of a different problem, if you would. The interesting thing with longer text is that transformer models typically have an upper bound on how much text they can handle. So you can argue that that's kind of like a weakness of transformer models in a way. And that is the case. But then if I think about the Model2Vec thing, right? Suppose I have a sentence with like 10 tokens. So token 1 all the way up until token 10. And if we have embeddings for all of them, right? Well, Scikit-learn still just needs one embedding over here. Like, we need one vector to represent the example. We can't have 10. Like, we need a single thing. So what typically happens here is there's some sort of pooling that's happening. And at the moment, they're just taking the mean. That's not the worst idea. But you can imagine, if you take the mean, right, that also kind of grays out some of the signal. Like, if suppose there's two words in there that are super duper important, those directions, those vectors, they do have to blend with everything else in order to get this single vector representation out. So you could kind of wonder, well, how much better or worse are we off if we then do this vector thing, because we do have to do this pooling in some way. So we are going to lose some information there. And you can also hopefully imagine, like, for 10 tokens, that might be fine. But if you have a sentence with like, or like a text with like 100 words, then this averaging is really going to reduce a lot of the information. And that's, again, this is kind of what the attention mechanism is for. The attention mechanism hopefully can tell you which tokens matter more, but we don't have access to that anymore. We just have Zipf's law that hopefully sort of compensates for that. So for this one, for the last one, I figured, okay, I'm just going to go for the 20 news groups thing inside of Scikit-learn. It's, and let's actually, if I look at the text, we can just have a look at one example. Like, these are, I think they are emails, but they are about like things that happen, things that could be in a newspaper. And then you have to figure out, like, okay, what category of news is that? And there's like 20 categories of them. That also makes the benchmark kind of different and interesting. It's no longer binary classification. It's like a lot of categories. But one thing you can also just kind of see is that there's just this is like, some of them are like kind of short, I guess, but there's definitely some longer ones in here as well. And what's also kind of interesting about this one in particular is that we have lots of these like symbol characters and stuff, and with the @ symbol over here. This is not necessarily perfect English. This is definitely kind of more like an email and some internet stuff in there as well. So one thing with this data set, it's also a fair bit bigger. Let's actually, how much? This is a somewhat larger data set, right? Yeah, so there's like 18,000 examples or so. So I ran the benchmark, but it was just also because it has like 20 labels, it could be. I just noticed the ensemble models were just too slow on my machine. Like, I got impatient. So I am only running the benchmark for logistic regression on this one. Definitely something to keep in mind. Also, remember, this data set is also not necessarily a perfect representation. But okay, you run the thing. And then the charts start looking a little bit more interesting, if I'm honest. So, same as before, but there's a few things that just kind of are interesting. The first of it is like, because there's 20 categories, the accuracy number, it's super easy to get a low accuracy, because if you're just playing the guessing game, well, then you get 50% accuracy already, if it's binary. But in the case of 20 labels, if you play the guessing game, the highest you can get is 5%. So you can very clearly see on this data set, if I have small dimensions, that the score is like pretty bad, but that it gets like, it has a nice curve to it, this one. I think this is partially because it just has more examples, and therefore there's more statistical power when I get a number out of the system. But hopefully you can also imagine that if I didn't have 20 categories but way less, then we wouldn't have as small of a number over here. Another thing that's also interesting with this one is we can now actually see, especially when we zoom in, these dotted lines are the ones where Zipf's law is doing its thing. In this case, we do see that Zipf's law really has a good influence. That's like a good percent on top, and it's pretty consistent as well. Maybe not so much in the smallest area over here, but also over here there's like a 2% boost, and over here it's also kind of like, yeah, it's at least 1, but maybe more, right? Okay, so that's pretty interesting. Whether or not Zipf's law has a huge impact seems to depend a bit on the task. And one thing that I can also kind of imagine, if I think back about the first data set that I tried it on, the one that should carry some statistical power, that task is just super duper easy. Like, whether or not this sentence is about a new data set or not, basically you got to look for 5 keywords and then you're done. In this case, that's not gonna cut it. If I were to compare this, like the best model over here, and I guess I could definitely go for like higher dimensions, right? But if I go for like a relatively small dimension here, like, you can definitely see we can add some more dimensions. That's the benchmark I could continue to do. But if I were to compare that to that's something I thought was interesting on this data set too. If I just look at the normal transformer models, how well they fare on this data set, it's definitely better than what I see over here. I might be able to improve upon that when I add more dimensions here, but okay, fair enough. But because there are so many of these weird characters in this data set, the count vectorizer model just blows the transformer model out of the water in this one as well. And I thought that was pretty interesting too, actually, if I'm honest. Did not expect that. But it does make sense if you consider all those weird characters that appear in this dataset. Suddenly, the bag of words approach might not be the strangest idea, because you just gotta hope that the transformer model has been trained on similar datasets. So maybe this is not the case. So, I think so. From concluding from all of this, like this is just a bunch of benchmarks that I ran on my own data sets over here. And one lesson that I do learn is that the results can really vary widely, and that depends mostly on the data set that you are running. So it could very well be the case that you have a data set where the count vectorizer bag of words thing is just fine, and throwing a transformer at it's not going to cause too much of an impact, and neither is maybe the Model2Vec thing, and that's fine. There does, however, seem to be a thing, and I kind of saw that. Oh, my mouse is over there. I guess I kind of saw that over here, where the count vectorizer model, it did kind of okay, but you can get like a good percentage nudge if you do the Model2Vec thing, while still being super duper quick. And that's a win. Like that's the main thing I just kind of want to point here. Like I do have evidence that for some tasks, this Model2Vec thing might actually just go ahead and work. Probably, if you're going to do a sentence transformer thing besides that, it could very well be the case that the boost you get from a sentence transformer is bigger, but the win lies in the fact that it's still lightweight. And that's kind of something that I do think makes me rather enthusiastic. Especially because this thing, in the end, is also, all about subwords and stuff. I can definitely imagine some sort of script in my pipeline that's going to just distill a bunch of these big models. Once that is distilled, I have something lightweight, and that can maybe add like a percentage boost to my scikit-learn thing. And it's quick, neat, like super cool. But run the benchmark yourself, because the results just seem to vary a bit. That's the main advice that I got here. One thing that I do want to mention, I had a chat with the maintainers of this tool, because, I really do think the results here are kind of reasonable, but I also wanted to talk to them like, hey, this is how I experienced it. How do you folks experience it? One thing that they also pointed out to me is that they are a little bit concerned about the benchmarks, in the sense of they are aware of this pooling phenomenon that could happen. Like if you have a very, very long bit of text, will this approach still work? So they are interested in relooking at some of their benchmarks, where they really pay attention to the length of the text that they're going to be classifying, because maybe it's not fair to compare long text results with short text results. If the length of the text can have such a big impact, it would probably be good to dive into that a bit more to understand it better. Finding great benchmark data sets remains hard, but I did think that was like a very mature observation on their part as well. Like they were concerned about that, so was I, but they were also aware of that. The final thing that I also discussed with them, that they were actually working on this, which I thought was pretty cool too, is I actually saw an opportunity to make this even more lightweight. So the methodology is sound. I like the idea. All that stuff is super duper cool. But if you have a look at how I have to load this thing, if I this bit. So you'll notice here that Model2Vec over here, it has to load the static model object, and that static model object does the from pre-trained thing. So far so good. This kind of works. But if I then go to the Model2Vec repository and I look at their pipeproject.toml file, oh, I think they already made the change. Yeah, okay, they already made the change. Good, super cool. So I think a week ago, when I first looked at this, I think transformers was a core dependency of the project. That makes sense, because if you're going to distill a transformer model, you need the transformers library. So that all feels good. But transformers, the library, comes with PyTorch. And when you add those two things together, I think that's like 1.5 gigabytes of disk. Like your Docker container is going to be pretty big. So I was talking to them like, hey, would it maybe be possible that you do your distillation in one environment, but then when you want to run the model, that you then do that in an environment where you only have NumPy? And I was discussing that with them, and they were surprisingly enthusiastic to implement that, because they totally agreed that would be like a great feature. I talked to them on their Discord for a small bit, and and there's no pull requests anymore, so I think they merged the thing. I mentioned it to them, and within a day they started working on this basically. And I just want to give a shout out because that's super duper cool. So what I believe you can do, and I might be on the docs already, but what you should be able to do either right now or very soon is that you're able to sort of do your distillation in a environment and then do your inference in a environment that doesn't need PyTorch. And again, from the perspective of scikit-learn pipelines, that is amazing because it would be such a shame if I needed to download PyTorch in order to get my scikit-learn pipeline to get that 1% extra accuracy. That's just going to make the pipeline slower and also make my virtual environment just blow up. Not to mention memory. So yeah, that's my review. It's just pretty like it's hard for me to guarantee that your pipelines are going to perform better because of it. But the idea is just sound. Like it feels like a nice trick. So what I am gonna do is maybe not today, maybe sometime next week. I am gonna seriously consider adding support for this in Embedder. That's a tool that I made for scikit-learn to get more embedding models into the mix. Because I just think the idea is really good. Another thing that you can also get like see in the future is that maybe we're gonna have more of these like distilled embeddings that you can sort of download from the internet. Like maybe some of those models I think you can already host on Hugging Face these days. But yeah, you're still like in the maybe you throw away 5% of the speed, but you if you also gain 5% accuracy, like stuff like that might be possible with this, and that's just kind of nice. I'm super enthusiastic for this. And also cool to see that Sentence Transformers has added support for it right away, because it also feels like that might make a whole bunch of benchmarking easier as well. And this is the point in time where we're almost at time, but there's people asking questions, so I'll definitely start asking there as well. So Tom is asking, like, was the performance of NumPy-based versus PyTorch-based inference tested, by the way? Not to my knowledge. Like, I'm pretty sure they will come up with some numbers. That said, at some point, I'm pretty confident the CPU story will just be fast enough, but it's the size of the Docker container that at least I was worried about. Like PyTorch is not a small library, and if you need that in your Docker container just to do a like linear bag of words embedding stuff, that does feel like a heavy dependency when you consider that NumPy should just be able to do it. And again, when I'm considering the perspective of I am thinking about a scikit-learn pipeline, scikit-learn depends on NumPy, so I need NumPy anyway, but scikit-learn does not depend on PyTorch, and therefore if I don't need PyTorch, that's a plus. So it's more of a memory size and a Docker container size thing that got me thinking about that, not so much the CPU speed. I would be somewhat surprised if it was significantly faster or slower, but as always, if it's faster or slower, that's probably because of like some sort of CPU instruction that's misconfigured or something like that. Not the. I can't actually. I can't imagine one thing in the sense that PyTorch does have some extra support when it comes to multi-core things, maybe more so than NumPy. So that could be like a fair reason. But I talked to this group on their Discord, and they seem mainly interested in keeping the CPU quick. Like they don't do a lot of GPU stuff. So I would be super surprised if NumPy would be like way slower. Matthijs Vogelzang is saying, like, could also be interesting to try a predictor that includes bag of words and some vectors in addition and see if it captures a distance signal. Oh, it's funny you mentioned that. So this archive front page thing totally does that, by the way. What I'm doing here is I've not changed the model over here yet. But the model I'm using over here is a sentence transformer plus count vectors on top. And the reason I do that is because I was kind of curious, like, hey, maybe there's just some super specific words that end up being super duper important. So let's just add a count vectorizer to the mix. And then it's kind of a nice trick, really. So like if you've got, let's say you've got like your sentence embedding over here, and then you've got your count vectorizer embedding over here. This count vectorizer thing is sparse, right? It's like a super sparse thing. So that means that this entire thing is also going to be super sparse in the end. But if you follow it up with like a logistic regression, the logistic regression scikit-learn can totally deal with that. But kind of the nice thing here is if you add both of these together, it's the logistic regression's concern to figure out which examples are sort of more or less important for your task. And the reason why, at least theoretically, I think that having count vectors next to your sentence, like next to your embedding, why that makes sense, is partially because my former employer Raza did that a whole bunch, and I'm assuming that they have a good reason to do that. But also because this is an easy task, this new datasets thing. I've also got this other task that's already a whole lot harder. Like, can we detect if an abstract is about data quality issues? That's already a fair bit harder. So maybe the logistic regression is going to have to lean more on the sentence transformer stuff there than the count vectorizer stuff. So again, like having both in your pipeline is super duper sensible, because then logistic regression can figure out which of the two embeddings to listen more to. And in my case, if you have multiple binary classifiers, you can just use the same pipeline again. Very convenient from a developer experience standpoint. Tom is saying some interesting things. So Tom is saying that he's probably going to keep the torch-based inference in sentence transformers right now because there's already torch dependency, and he can fine-tune his embed. Yeah, okay. So those are. So I'm thinking about using Model2Vec like standalone inside of a Scikit-learn pipeline, given that Tom's perspective is, hey, I maintain sentence transformers. There's already PyTorch. Do I need to implement the NumPy thing for this? I would agree there's not really a good reason to, unless there's evidence that it's way quicker, but I would be somewhat doubtful. I think PyTorch and NumPy should be somewhat on par there. And I guess it's like a final question. How do we keep the contextual aspect of transformer embeddings, although we have one static embedding for each token? Well, so you don't. That's the thing. The trick that they use is really just PCA and Zipf's law. And I can kind of argue why Zipf's law might make... I mean, so you do have the fact that that transformer model, if you think about like how normal word embedding models are trained, it is really, oh, we've got all these tokens and we're going to predict the next word, and that's the system, and that's going to give us our embeddings. Transformer models have a very different way of training, so it's also very plausible to me that the embeddings you get out are just also different and maybe more useful in general. But if you then combine that with Zipf's law, like that's the tokens that appear super frequently, maybe we gotta tone them down a bit. But the ones that are super infrequent, maybe the ones that are super infrequent, those are the ones that tend to be the most important. Like maybe that could be like a way to think about it. So if I think of like bank of the river and money on the bank, of the and on the, Zipf's law would totally remove the importance for those two terms, which would leave the term money and bank or bank and river to be super important in that sentence. And yeah, I can see a bit of logic, sort of that it's still able to keep some of the context in line there. As always, check this on your own data set. Like I'm not going to be able to claim that this will work for every single data set out there because my benchmarks confirm that's not the case. However, I really do appreciate it if more lightweight stuff comes around. We need more lightweight stuff, and having this super cool technique such that we can definitely still use something that sentence transformers does, but in a nice little bundled together way that's lightweight with just NumPy. I mean, sounds like a cool feature to me. So that's like a welcome addition to the ecosystem. So super duper cool. Let's do more of it. Yeah, so the Model2Vec output is always the transform. So yeah, so what Thomas. So there's questions again. People are asking like, hey, if I have a sentence. So let's draw that one last time. I mentioned that earlier, right? So I've got token 1, let's say up until token 15, because I've got 15 tokens in my text. For each of them, I would also have an embedding, right? Oh, E15. And you would probably do some pooling. So in that case, you would probably take like the mean of all those embeddings, and that would be the embedding for the entire document. Final comment on that, actually. So I talked to the maintainer. What the maintainers are gonna maybe do this one benchmark. This is a trick that I've seen work pretty well inside of Spacey. So Spacey does this. Spacey is also dealing with this phenomenon of, hey, a sentence has multiple embeddings. How do I turn it into a document embedding? And what they do in the pooling is they do the mean pool and the max pool, and they concatenate those. So you can imagine, if you look at their, not every part of their system does that, but there's a few places, like the SpanCat model does it, where you've got like the mean pool and the max pool, and that's going to sort of define the embedding. The thinking with the max pool is that sometimes if there's like one, there's like one direction that's really pronounced, let's say. So there's like a 300 dimensional object, but there's just one index that has a very pronounced value, one that's pointing in a certain direction, super duper pronounced. Okay, if only that word is super pronounced in that direction and all the other words have like near zero values, that direction is going to get smaller and smaller and smaller and smaller. It's going to maybe disappear if we have more words. If you keep the max around, though, that you can still remember there was one word that was really pronounced out there. Now, combine that with Zipf's law, then you might be onto something. So this is also something I discussed with the maintainers of Model2Vec, and they thought it was actually kind of interesting and maybe worth a benchmark. So I would expect them to do it. I am not going to pressure them to, but it sounds like that might be a cool idea on their side as well. They also mentioned that their implementation of this should be straightforward, so they're going to maybe try this. That's maybe that might also be yeah, something that the future will bring. I think it might, like Embetter, the library that I maintain on behalf of Scikit-learn. Embetter does this. I'm sorry. Embetter, the library that I don't maintain it on behalf of Scikit-learn. Embetter, the library that I maintain that is a plugin for Scikit-learn. If they have word embeddings under the hood, this is the pooling that I do. So I would not be surprised if the Model2Vec people start doing something similar as here or well. Yeah, and there's extra stuff that you could do. Let me just see. Could also be interesting to add prompt to it. Launching dataset token, maybe generate embeddings that are more tweet. Yeah, I mean, so the thing is, in the domain of NLP, there is no shortage of stuff that you could do with embeddings. I think the whole point of this Model2Vec stuff is just that there's something reasonable and lightweight that you can consider as an alternative, and that's a welcome thing. Again, like if I'm going to do more benchmarks with this, I will probably try to find a good tabular data set where like one of the columns is text, and like that'll probably be the benchmark that I'm interested in at this point. But also remember, if you're ever going to do like benchmarks of NLP and you're doing classification, for God's sakes, logistic regression and count vectors, or TF-IDF, just do a sparse feature representation and give that to like a super simple model. Run that benchmark, like that's the base rate. And also in the benchmarks that I just shared, you can see that those models still perform pretty okay on a lot of these tasks. So you can often keep things simple. This is a nice lightweight way to maybe have things that are just slightly less simple, but not that much more complex either. So this is cool project. Next week, we're going to come back, but next week I'm probably going to do the most opposite thing in NLP that you can imagine. So instead of like favoring linear models, next week I am going to be discussing a RAG application. And we're going to dive into that a bit because I think it's like interesting stuff a colleague of mine did. Guillaume, he wanted to build like a RAG retrieval system on top of the Scikit-learn documentation. And he did the thing proper, and you can also look at Scikit-learn as like a pretty good documentation resource. It's big, so you want to do retrieval tasks on it, but it is like decades of work went into that thing, so there's a lot of knowledge. But then it turns out, even if you have immaculate documents to sort of fetch, it is super duper hard to build a proper RAG system. So what I'm going to do is I'm going to run the RAG system myself, and we're going to sort of poke around at it. And then I'm also going to interview Guillaume about his experience in the podcast, because you would kind of assume that doing the RAG thing, one of the hard parts there is that you do need immaculate data maybe if you want to do retrieval well, and this is true. But immaculate data is, even when you have the Scikit-learn docs, not necessarily straightforward. I ran a quick benchmark on it, and I'm going to have to spin up some infrastructure to make this thing performant, but I'm probably going to, and maybe for some weird reason, I need to delay this a week, but one of the next live streams that I'll do, probably next week, will be about this RAG system that folks internally have been playing with to see if we can do something on top of the Scikit-learn docs. And the short story is it's hard. It's sort of the summary, but I'm eager to show some of the lessons that we've learned there. Cool. People seem to have enjoyed it. Thanks for listening. I'm off to have lunch and take care of the kid downstairs. Y'all have a good weekend. And if you haven't already, this week or next week, I can suggest we will be making some announcements. So if you're interested, be on our Discord, discord.probable.ai, and you can be part of the conversation if you're interested. And also, if you haven't already, yesterday I released a new podcast. In this podcast, I interview the co-founder of the Marimo Notebook project. It is definitely one of the more fun conversations that I've had, not just because designing Marimo is interesting, but turns out the guy also worked on TensorFlow 2 as well as CVXPy. So he's got like a very solid technical background, and it's a fun conversation that demonstrates how both TensorFlow and CVXPy help to inform him on how to build and design a new notebook system. So the particularly interesting conversation. Hope you like it. Check out the Sample Space podcast if you haven't already. I'm gonna stop talking and I'm gonna start having lunch. Y'all have a good one.